Hello everyone, my name is Danijela and welcome to tonight's webinar on geometry and measurement. Firstly, let me just start this webinar by saying that geometry and measurement module is not one that you can completely lean on your CAS calculator for a lot of the thinking, so to speak. Not that you can really lean on the CAS for all of your thinking anyway, for any of the modules, but in geometry and measurement specifically, you'll have to have a very strong command of the content, and the CAS will support you with the execution and efficiency. Okay, let's move to the next slide. The first tip I want to give you with the geometry and measurement module is that practice drawing your diagrams. We teachers don't like to see diagrams, teeny tiny ones, that we need a magnifying glass to read the angles or read your measurements. Really make sure that you make use of your space, draw nicely and clearly. Even if you don't have a ruler on you, you can still draw an accurate semi-to-scale representation of the context you're given. Another big tip I can give you is really know your angle facts. So those are the ones that are on the screen right now. Know them really well. They'll come in handy during this module. Now, for the geometry and measurement module, we're going to cross over now to the CAS screen. 1 second. There we go. Hopefully you can all see that one. Make sure that your settings, your document settings, are set up appropriately for this particular module. And in general, for further maths, the settings should be quite the same. So if we click on the Doc button and you go to Settings and Status, and you go to Document Settings, what you should see is that the angle should be in degrees and the calculation mode set to approximate. Now, if you're doing methods as well as further maths, sometimes you'll have to change these settings. So the angle might have to be in radians instead of degrees. And the calculation mode for methods is most of the time exact. So be really careful with the settings on your calculator. Okay, just going to go back to my PowerPoint for a moment. Let's start with problem 1 in the handout that was provided for you. Now, problem 1 I've purposely put in there to show you a little snazzy trick your CAS can do, and that is convert units. We all know that conversion of units can sometimes be one of those things that are, especially in the heat of the moment when you're sitting in an exam, when you're under pressure, can be quite tricky to do. Luckily, your CAS does all that thinking for you. So this is an area where you can really utilize your CAS really well. So there's a few different units we want to convert there, and I've got a screen dump here of how the CAS does that. But we're going to cross to the CAS screen in a moment so I can show you how to do that, and you can watch how that's done. On a side note, you will be also given this PowerPoint, so you can use that as well if you like. Let's go over to the CAS screen now. Okay. So for the unit conversions, the first one, and I've got a piece of paper in front of me, I'm not just super great at memorizing, is 2.58 kilometers into centimeters. What we're going to do is write 2.58 into our calculator, and then we need to tell it that it's in kilometers. So if you click on the catalog button, which is over here on the right, and the third tab across the front here is the units tab. I've already selected it. As you can see, I've already been playing with this tab, so it's already selected. But you'll have various other tabs in the catalog menu option. Here, what we're going to select, because we're doing in kilometers, is length, and we're going to go down and find kilometers. There it is, and we're going to click that, and it gives us that. Then what we need to do is tell the calculator to convert it. So if we go back into the catalog button, and if you go to the fourth tab across with all these symbols, you'll find this kind of triangle right pointing triangle symbol, that is for conversion. So we're going to select that one. And we're going to tell it to convert it to centimetres. So to find centimetres, we can go back into our catalogue, go back into our units for, and then go back into our units for length and find centimetres. Press enter, and there you go. 2.58 kilometres is 258,000 centimetres. Now, a shortcut is that you don't have to necessarily go into the catalogue button every single time. Let's do the next one without doing so. Well, without doing so much. 164 millilitres, millilitres into litres. And if you note, the way that the CAS knows that it's a unit is it's got this underscore in front of the unit symbols. So what we're going to do is find the underscore button. And the underscore button, the underscore symbol can be found in this extra symbols button here on the bottom right-hand side. And there it is. 164 now millilitres. We can simply write with our keyboard down the bottom, ml. Now we're going to need that conversion button. So we're going to go back into our catalogue, tab to the fourth tab across, select that conversion, and then we're going to type in underscore litres L. Now, I'm using the software, so I'm not on the handheld device. So underscore for me is really simple. I'm just using my normal keyboard. I do encourage you to use the software if you have it at hand as well. It's much, much quicker. So let's do that. So 164 mils is 0.164 litres. We'll do a couple more. Now, I've got another one here. I've got metres cubed into centimetres cubed. 3.29 metres cubed into centimetres cubed. Now, metres cubed is a volume, but if I go into my catalogue and try to find it under volume, which is here, and as you can see, under units, you've got several different types of units. You've got constants, length, area, volume, time, velocity, temperature, and so on. There's a lot of different units. More than ample, more than everything you need for further maths. So under volume, you can see you've got cups, gallons, litres, millilitres, pints, tablespoons, teaspoons. Great for if you're cooking. You don't need your phone. You use your CAS. However, it doesn't have what we need, which is meters cubed. But we know meters cubed is just meters to the power of 3. So you can simply write that in, and that's fine. The CAS will understand that. And then go to your catalogue, do your conversion, and we want it in centimetres cubed. So underscore centimetres cubed. There we go. Now, it's brilliant as well for time, and I'll just quickly show you that. So 3.4 hours into minutes. So 3.4 HR into minutes. 204 minutes, and so on. So you can play around with that unit conversion feature. Very handy, and something not many people know about. Okay, I'm just going to go back now to the PowerPoint. All right, and we've got the other ones there as well to have a look at. Let's do problem 2 now. Emma is hiking. She walks 27 kilometres from her starting point on a bearing of 45 degrees until she reaches a campsite. She decides to take a small break and then continues the hike, walking 14 kilometres on a bearing of 300 degrees, etc., etc. In this problem, you've got a word problem. You don't have a diagram. You have to draw the diagram. Be very sure to draw a clear diagram so that when you're labeling things, everything is nice and clear. Let's do this. Let's put the first piece of information in. She walks at a bearing of 45 degrees. Now, these are true bearings. That means they start from north and go clockwise around. And she walks for 27 kilometres to a campsite. Now, notice I have put in a few angles there. Knowing my alternate angle facts, I'm able to know, well, that it's 45 degrees everywhere, basically, in all those angles there. So then after that, Emma decides to go on a bearing of 300 degrees. So 300 degrees clockwise is 60 degrees away from being a full rotation. So that's 60 degrees away from being a full rotation. And I've just labelled that as 60 degrees to be able to draw my next path. Hopefully everyone can see what I've done there. So 300 degrees from north clockwise gives me 60 degrees from north anti-clockwise. So I've got my 14 kilometres there, and then I've reached a lake. And then from the lake, she heads directly back. So this is my diagram, and hopefully you can draw something as clear as this. Now the question part A does not require the CAS, it requires you to be good with your angles and have a very clear drawing. Part A says, what was the bearing from the lake to the campsite? Now the from and the to is really important. So we're going from the lake to camp. Make sure that you verify that your bearing is from the right location to the right location. So if we're looking at the lake, we need to know from north, clockwise, all the way to that line that joins camp to lake. So how do I know that that's a 60-degree angle there? Well, I can use my alternate angle factor. Then, knowing my alternate angle factor of 60 degrees, I know that I've got 90-degree angle there, plus another 30-degree angle to make up the 120 degrees. So the answer to the first part is 120 degrees. True bearing. Now, what is the total distance Emma has walked in kilometres? Now, the total distance relies on us having figured out x. So x there is the unknown length. And as you can see, we've got two other lengths given. We've got only one internal angle, which is that angle at the campsite, which is the 75-degree angle. And the two lengths, and the 75-degree angle is between the two lengths. In this case, we have to know that we have to use the cosine law. And for that, we're going to jump to the CAS calculator again. I'm just going to go on to the next problem, problem 2.1, to show you how to use the CAS calculator for this. So what we're trying to find is a length. So we're going to use the solve function. So I've just typed it in there. Otherwise, you could go menu, algebra, solve. And we're going to type in the equation that we know, the formula we know, the cosine rule. A squared, and let A be the value that we're looking for, which is that x length between the lake and the start. And then it's B squared plus C squared, so the other two lengths. So we're going to go 14 squared plus 27 squared minus 2 times 14 times 27, because it's minus 2 times B times C, times the cosine of the angle A, which is the angle between lengths B and C, which we know to be 75 degrees. Now, because our calculator is already in degree mode, we don't have to tell it that's a degrees value. And we're solving for A, so we have to tell it what to solve for. Press enter. As you can see here, the calculator spits out two possibilities, and it gives me the fact that it could be negative 27 or thereabouts, or positive 27. Using your common sense, you can determine that length, x, should be positive 27. Now, this is just simply using a calculator page, which you should all be familiar with by now. But I also want to show you something I've prepared earlier, just to flag it as a really, really nifty tool you could use to save yourself some time, especially for things like the cosine rule or the sine rule, where you know that that's going to come up in your exams. That's almost a guarantee. So you can set this up for your exams to save yourself a lot of time in typing out these long formulas. So what I've done in page 2.2 up here is I've set up a notes page. And I'm not going to go into the specifics of a notes page today because there's a webinar coming up on the 16th of September by my colleague Craig, which will go into it in a lot more depth. So I really encourage you to register for that webinar. It's going to be fantastic. What I've done here is I've set up a notes page, like I said, and I've given it a title, Cosine Law, if looking for, cosine law should be, if looking for length A, for a length A. So what I've done is I've pre-entered the formula, the equation that gives me my length A down the bottom here, and I've assigned B as being certain values and C and AA. What does AA mean? Now this is another interesting thing. Usually when we denote lengths and angles, usually we would denote the length as a lowercase a and the opposite angle to that length as a capital A. Unfortunately, you cannot do that in a CAS, in the TI-Nspire CAS environment, because it does not differentiate between lowercase and capital letters. So what I've done is simply, for angles, I've put in double A. Or you can think of it as angle of A. Or you can, it doesn't matter, because what the CAS is reading that as is a separate variable, reading it as a variable called AA. Okay, so I've assigned B to be 27, the length of B, C to be 14, and angle between those two, AA, to be 75 degrees. Now, what's wonderful about a notes page is that if you've made a mistake and you've accidentally typed in the wrong number, you can go back any time and fix it up. Let's say I was supposed to type in 16 instead of 14. I can fix it up and it automatically changes the solution I get. You can also save this document into your CAS directory and bring it up for exams, and you have it there ready to go. And if you properly label it like I have, cosine rule, if looking for length A, you know exactly what that document's doing, so it could be really handy in an exam situation. So there we've got 27 kilometres is the value of our missing side length. So let me just go back to the PowerPoint. So we've got X there is 27. We've got another 27. And remember, read the question. It says, what is the total distance? So it's not asking me what X is. It's asking me what the total distance that Emma has travelled is. So you have to add up 27 plus 27, which is 54, and then another 14, which is 68 kilometres. So the answer to that one is 68 kilometres. Okay, let's move on to problem number 3. And I've chosen problems or questions that tend to cause a little bit of a few issues with students that students do not often answer really well in exams. I've chosen them specifically for that reason, so that you can get practice in the tricky questions. Here we've got a triangle ABC, and it's given us some information about triangle ABC, but it hasn't drawn it for us. So we have to determine how to draw this triangle. AB has a length of 5 units, BC has a length of 8 units. So you might start by doing something like this. AB, here's my 5 units. BC, here's my 8 units, and let's join those two up. And we know that angle ACB, which is that angle there, is 36 degrees. Most people would draw something like that. Okay, it doesn't have to be in that orientation at all, but a triangle like that. Now the question asks, which of the following angles could not be another angle in the triangle ABC? Okay, so what we're going to have to do is work out the other angles. For this, when we've got this scenario, we could use the sine rule. So I'm going to go back to the CAS right now to use the sine rule there in that environment. I'm just going to go over to page 3.1. Now, in this page, we're just using a basic calculator page, and we're going to solve for the angle, I'm just going to show you which angle we're solving for first. We're going to solve for the angle at A, the one opposite 8. That's the one we're solving for first. All right. So I'm going to use solve, and I'm going to set up my sine rule, which is sine of A, which is the one we're looking for. Sorry, 1 second. Sine of A on, and if you remember, if we go back to our diagram, actually that was across from the side length of 8, and I'm going to put in a fraction template here. Oh, wait, one moment, I need an equal sign. An equal sign, sorry. Equals fraction template again over sine of 36 degrees it was from memory. No, I've got it on paper, don't worry, I'm not memorizing. Over 5. So what I'm solving for is that angle of A, and I need to tell the calculator what I need to solve for. Now what it spits out is something that looks quite unintelligible. I'm not sure what that means. It's confusing, it can't be right. Okay? Well, it is actually right. Some of it's right. But with angles, the CAS calculator doesn't know what quadrant of angle to locate your angle in, which is what you might not understand what that means. But for the purpose of further maths, whenever you're solving for angles, you cannot use solve if you want a clear answer. You have to, and I'm just going to go back and select this and bring it down, copy it down to the next line. You have to use a function called numerical solve or nsolve. And I'll show you what happens when I write just an n in front of solve. Ta-da! It spits out something that makes more sense. Okay, so remember, when you're solving for angles, if you don't use nsolve, you might get this confusing solution. Just copy and paste it and put the n in front of the solve, and you'll get something that looks much more intelligible. Okay, so we've got 70 degrees. So if we go back now to our PowerPoint, that means that that angle there is 70 degrees. Using the fact that we know the sum of internal angles of a triangle is 180, we can solve for that angle. So we definitely know that 36, 70, and 74 definitely can be a part of that triangle. So what's with the other three then? 110, 34, and 22 degrees? Well, so far, I'm pretty sure none of those can be part of that triangle, or can they? Obviously, 3 answers cannot possibly be all 3 correct. And this is something that most students completely forget to consider, that there is a case called the ambiguous case of the sine rule, where you could have drawn your triangle that looking something like this. And the kind of go-to triangle that students draw is the other one, the one with the acute angle there. But this one is also possible. And it's possible when the length next to the angle given is longer than the one across from the angle given. So the 8 is longer than the 5, so that makes the ambiguous case possible. So now we've got this other possible way that we could have drawn this triangle. How do we find the other possible angles? Well, given that the triangle we've now drawn with A dash, and B is an isosceles triangle, that would mean that that's also 70 degrees. And that's very important. And then that would mean that that other angle, which makes up 180 in a straight line, is 110 degrees. So automatically we can see that 110 degrees is a possible angle of the triangle. And then we can find this angle, which is simply using the sum of interior angles is 180 degrees fact to subtract 110 and 36 from and get 34. So that leaves the correct answer. The only impossible angle is 22 degrees. Like I said, I chose this one because very, very few students in an exam situation actually consider the ambiguous case. All right, problem number 4. This one is about time zones. And it says that all towns in the state of Victoria are in the same time zone. Mallacoota, which is on the east coast, and Port Fairy on the other side of Victoria are 2 coastal towns with quite different longitudes. And longitude is, I'm just going to write, usually we get a coordinate for latitude and longitude, always actually. Latitude comes first, which tells you the north and south, the degrees north and south. The longitude comes second, tells you the degrees east and west. Longitude is the only one that's responsible for time difference. So that's the only one we have to consider in any time zone type questions. We have to know that 15 degrees in longitude corresponds to 1 hour time difference. And that actually means, if you can remember, that 1 degree in longitude corresponds to 4 minutes time difference. That might be a very handy thing to remember as well. Mallacoota to Port Fairy, if we look at the longitude and longitudes only, 150 degrees minus 142 degrees, there's a difference of 8 degrees in longitude. Now, we're just to save a bit of time, I could have done this in the CAS, but this is pretty simple to do on CAS. So I'm just going to show you how to do it on the PowerPoint. Got 8 degrees difference. 8 degrees out of 15 degrees is the proportion of the hour. So 8 out of 15 times 1 hour, or we'll just put it in 60 minutes to give us a nice minute amount, is 32 minutes. That proportion, so 8 out of 15 is 32 minutes of the hour. So that's how we know what the time difference between those 2 towns is. Now, you have to remember that the more east a town is, the more ahead it is in time, and the more west, the more behind. Therefore, Mallacoota will have their sunrise earlier, because it's more ahead, than Port Fairy will. Mallacoota is more east, therefore more ahead. The sun will rise 32 minutes earlier in Mallacoota. If we do our calculation, so if it rises 7:03 a.m. in Port Fairy, 32 minutes earlier, if I've done that correctly, it is 6:31 a.m. in Mallacoota. There you go. All right, like I said, you're going to get all this in videos and the PowerPoint presentation. You can go through it later at a slower pace if it's too fast for you right now. And the last problem for today's webinar is this one, which is about a horse racing track pictured in green. Now, the diagram looks quite complex at first initial glance. And the question says this horse racing track needs to be completely enclosed in fencing. Okay, so it asks how many meters of fencing are required to complete this project. First thing, always when you hear fencing, you should think perimeter, not area. And we can break down the fencing into bits. So here we've got a fence that requires 2 curved parts, which is kind of the outer circle, the inner circle, and the 2 straight ends, which may be the ones that students forget to add on, the 2 straight ends that kind of close off the horse racing track there. The curved parts are both sections of a circle circumference, not the entire circle circumference. Obviously, it's not the entire circle. They're sections. To remind you, the circumference of a circle, that's the formula for it, 2 pi r or pi d if you prefer to work with diameters. But we've got radius given here, radii, so we'll just use 2 pi r. So going back to this, so we've got 2 curved parts and 2 straight ends. We've got the inner curve, we've got the outer curve, and we've got 2 lots of 15, why 15? Of 15 meters. That's how much we know that the track is wide. All right, so there's the curved part, the inner curved part. How do we find it? Well, it's given by the angle that we've got in the section of the circle out of 360, because we don't have a full circle. The full circle would be 360 out of 360, which is just a hole. We don't have a full circle. We have to work out the angle there and multiply it by 2 pi r. And r of the inner circle is 62. The radius of the inner circle is 62 meters. So I've got 62 there. Now, the outer circle, the radius is 62 plus 15. See, I've substituted that in. And the same proportion, the same angle applies. So what we do need to find is the angle there, and I've drawn it in red for you. How do we find that angle? Well, let's just go quickly to our CAS page now. I'm just going to add a new page, add a new problem. So what I'm going to do is go Doc, Insert, a new problem, add a calculator page. So it gives me a problem 4 at the moment. What we need to do is find angle theta. If you recall, we've got two 32-degree angles there in the isosceles triangle. So to find the missing angle in that triangle, we can go 180 degrees minus 2 lots of 32. That gives us 116 degrees missing from that triangle. Now to work out our theta, to show you that, theta there, so we've got 116 as a missing angle in our triangle. Theta is 360, so full rotation minus 116. So there we go. Our angle is 244. That helps us a lot with the proportion of the circle we've got. So I'm going to put 244 degrees out of 360. Proportion of the circle we have times the formula for the circumference of a full circle. 2 pi, pi is down bottom here, bottom left. And the inner circle had a radius of 62. There we go, we've got 264 there, 264 meters. And I'm just going to go up and copy this formula. That's a nice handy feature as well, the CAS. You can just arrow up, select what you want to copy, press enter, bring it back down, and we're just simply going to change the radius of the outer circle. So it was, if you remember, 62 plus 15, which is 77. Enter. We've now got 327.9 or so. So what I'm going to do is I'm going to go arrow up again, add this guy to this guy, and remember we have to add the two lots of 15, which were those straight bits that closed off the track. So after adding everything, we get an answer of 621.9 or 0.95. Now, the answer, the precision of your answer depends on the question. So if the question specifies to the nearest whole number or to correct 2 decimal places, you will know what to round this up to. So at the moment, I don't think my question has specified it. No, it hasn't, so I'm just going to choose to call it 621.95 meters. Okay, that concludes the webinar for this evening. If you have any questions, please ask them in the chat. I'm happy to answer them for the next few minutes.